Okay, hello. Welcome back. I am currently in my wind block with no one here, so I may have to pause this if somebody shows up. Here we go. Here is a GPE time graph. And what we're going to do, we've talked about there's an object that's released from rest near and above the Earth's surface, such that the object Earth's system's GPE as a function of time is shown on the graph. Which of the following graphs represents the kinetic energy? Assume all friction forces are considered to be negligible. Sorry, not negative. Okay, great. So this means that energy is conserved. Side note, not only is this shorthand for energy, but it's also the initials of Nolan, Ryan, Grillon. And if you think that it's just a coincidence that he has energy initials, and also if you think it's a coincidence that his middle name is Ryan for Nolan Ryan, you don't know me. Anyway, not the point. Okay, so energy is conserved. So that means, and it's released from rest, and there's no springs, nothing like that. So UG initial plus K initial equals UG final plus K final. Great. So basically, we know that the total mechanical energy of the system is 10,000 because it says release from rest. So this would be our K at rest is our initial K is 0 because there's no speed. So our total mechanical energy is 10. So if I let's use a different color. If I use the green to draw what the kinetic energy graph would look like, let me draw some points on here. So whatever this, the line is, the graph plus, at each point, the graph plus kinetic should equal 10,000. So we're going to start off with 0 kinetic energy at like this point here, right? There's about 9,000, so we're going to have 1,000. Okay. Here, how about this? There's going to be 2,000. I'll just hit where so there's 6,000. This will be 4,000. Here, there's 2,000. That'll be 8,000. Down there, there's 0. So this will be 10,000. So it should look, I'm just going to connect all these green dots. This is a curve, and it looks like that. Okay, you don't have to do all that math. Maybe you're just like, it's just going to be like flipped over, symmetrical, right? Fine. And that, oh boy, didn't mean to do that. That graph looks not like any of those until you get down to D. There it is. Next. Erase. Okay, the Atwood machine. 2 blocks connected by a string on a pulley. Okay, so they're connected. Block Y has more mass than block X. The string and the pulley have negligible mass. The pulley rotates with negligible friction. So again, energy conserved. Because the system is the 2 blocks in the earth. Great. What happens to the mechanical energy of the system? Great. So I just said that it was conserved. So let's take a look. Is that there? E mechanical remains constant. All right. That's because earth is included in the system and we have negligible friction. Okay. So there you go. Done. Boom. Also, we're doing the energy conservation unit. So there's that. But whatever. Oh, we got to erase. Okay, this one, I remember being like, when I did this. Okay, here we go. Here's an easy way to describe it. So we've got this happening in this graph. The mass slides down that incline. The length is 0.8 meters. The incline is 37 degrees. Do we need this? No. We don't need any of this, but we'll just put it in there like good little physics students. A graph is here. How could a student use the graph and information provided to determine whether the block Earth system, okay, so block Earth includes UG, whether it's open or closed. So how can we decide whether energy is coming in or energy is all contained? coming in or out, or constant? How do we decide? Well, here's the deal. And this is what tripped me up about this. It took me a second. This is the graph of, this is the full slide, meaning that we can say that V down at the bottom, so V final, is equal to about, you can estimate it, maybe 3.1 meters per second. The time it takes is about, T is about 0.51 seconds-ish. These are estimates. I'll erase. You can see where I got that from, right? Right there. Okay, so that point's about 0.51 seconds, 3.1 meters per second. Great. Really what we need is the 3.1 meters per second, right? So if we want to know if energy is conserved, we know up here, because it's released from rest, it only has gravitational potential energy, and down here, it only has kinetic energy. Okay, so here's what we got to do, right? We need to see if this UG initial is equal to K final. That's all. And if it is, great. So we have the information. Our final speed is 3.1. So we need to see if MGH, and we could figure out the H, right? Because we've got 0.8, it'd be 0.8 sine 37, is equal to 1/2 mv squared, the V being 3.1. Okay. So let's go through these. Use the known mass of the block. We know we don't need mass of the block. Who cares? Okay, use the known length of the incline and the known angle the incline makes to determine the height above the ground. Use the height and the object's known mass. No, we don't care about the mass. Again, we don't care about the mass because mgh equals 1/2 mv squared. Mass, goodbye. So we don't care. Use the known mass of the block and the initial velocity of the block to determine the initial kinetic energy, which is 0. Compare it with the final kinetic. No, we're not doing that. So hopefully it's D. Let's check it out. Determine the final kinetic energy as described above and compare it with initial gravitational potential energy. Yeah, it's D. Next. Good thing you guys can pause this video in case I'm next. Watch it again. No, this is the Atwood. Well, they're both Atwood. Great. The Atwood machine shown consists of 2 blocks connected by a light string. Look at that. The pulley has negligible mass and negligible friction. Yay. Blocks are released from rest. M2 greater than M1. Okay, down here, H equals 0. Which of the following represents the total GPE, UG, and total kinetic energy of the block Earth, yay, system as a function of H block M? Great. Okay, so let's talk about this, right? We know, here's what we know. We know that energy is conserved because, right, because of this yay. Energy, there's no friction, and I ran out of room. Conserved. And the block Earth means GPE, UG is included. Then we know energy is conserved. Yay. Okay, so first of all, when we go down here, let's start with that fact, right? We know, let's just assign random, well, let's just call this 1, 2, 3, 4, 5. Okay, so we know that the total energy is going to be 5 blocks. Equals 5, right? Because there's 0 down here plus 5. So they should end up at 5, right? Here we've got 0 plus 5 again. So this maybe. Energy's conserved here, that's for sure. If we go down, right, I think, let's see. Here, if we just check the last one, this is 1 right here, 2, 3. This is 4, so energy's conserved there. Fan-freaking-tastic. All right, here's the problematic one. Energy... Wait, actually, 1, 2, 3, 4. Yeah. So this is at 5. So we have initial energy of 5 blocks and then final energy of 1 plus 3 blocks. That's 4. See you later. See you later. And then this one's a possibility. Let's go back up. So here's the options we have. We have this one here, which means that after you finish letting go of the string, There's no potential energy at all, and it's all kinetic. And that's what this one down here means as well. And the second one means there's a little bit of kinetic and still a lot of gravitational potential energy. So let's look. If we were to drop this, right? Stop it. This goes up, this goes down. This doesn't stay on the ground. M1 doesn't stay on the ground. So M1 will now gains UG, right? So at no point in time is this block Earth system going to be without gravitational potential energy. It doesn't get to zero. They don't both end up on the ground. So that being said, we can cross this off because this, impossible. We can't have zero gravitational potential energy. And then this one, goodbye, because this part down here, impossible. We can't have zero potential energy. You could be perhaps thinking, if you're like, what? Maybe you're thinking about the right before mass 2 hits the ground, but this is a mass. So both masses included in the system. So it's got to be B. Fantastic. Nobody's coming to win block. You guys all know this stuff already. I don't know why I'm making this video. Nobody needs help. You know I like making the videos, so you know I love doing physics. All right, here we go. What's left? I got 2 left. All right, guys. So we've got this 2 kilogram box. It's on top of the incline release from rest. Great. So we know we've only got UG because V1, we'll call it 1, equals 0. Okay, great. I don't even know what the question asks, to be honest with you. It's an unknown distance. Great. The angle theta is also unknown. Frictional forces between the block and the incline are considered to be negligible. The block eventually slides down to the bottom of the incline after 0.75 seconds. The block's velocity v as a function of time is shown in the graph starting the instant it's released. How could you use the graph to determine the total energy of the block Earth system? Great. Okay, so first of all, get out of town. UG is included, right? Because Earth is included. Fantastic. All right, so let's think. So we know when it gets to the bottom, get over here. If we go back up, it's got a speed of 1.5, right? So let's call this 0.2. This is K only, right? Kinetic energy only. And this speed is 1.5. All right, pause. Mr. Morrison's here. You can hear him maybe. All right, to be honest, I don't actually know how much time just elapsed or what I was talking about. I think I said V2 equals 1.5. And we know that from this graph. So anyway, so we want to use this graph to determine the total energy. Yeah, all right, so B. We're going to use 1/2 mv squared final with m equals 2 and the final velocity 1.5. And that's going to be our total energy. And if you're like, why, how? Because that's all, it's all kinetic energy down there at the bottom. Okay, great. Next, last one. So this one, motion maps, whoa, throwback. A block slides across a flat horizontal surface to the right for each choice. The arrows represent velocity vectors of the block at successive intervals of time. So remember, successive intervals of time means equal intervals of time. Which of the following diagrams represents the situation in which the block loses kinetic energy? That means that the speed lowers, which means that the distance traveled in each time interval will shorten. So these all look pretty equal. So this would be a constant speed or constant velocity, whatever you want to call it right now. Same with this. Okay, so equal constant speed, equal constant speed. Here we've got long, shorter, shorter, shortest. So these are, this is clearly slowing down because the amount of distance traveled is getting shorter and shorter and shorter. So this is slowing down. So this would be C. D is when it's speeding up because in each second they're covering more ground. Okay. All right. That's it. Happy studying. Goodbye.